Oh, I'm on. I didn't realize I was on. Okay, let me give a quick, uh, just a real quick, like seventh grade algebra lesson here, and then also talk a little bit about this impulse and momentum that you just read about. Okay. First of all, quick algebra lesson. What if I have 6 minus -7? What does that equal? Well, as Jaime Escalante said in Stand and Deliver, negative times a negative is a positive, right? So this is my impulse discussion here. This equals 13. So, and you got to remember that impulse and momentum are vectors, and so that means that's important that we keep our vectors, and that means it's important that we know that direction matters. Okay, let me get that out of the way. That direction matters. All right. So classic case. Well, let's try another one. Let's try -7 minus 6. Well, that's -13. Okay. Um, so here's an example. Let's say a baseball is coming in at let's say high school level 45 meters per second. That's actually pretty quick. In the negative direction. So the baseball is coming in this way. All right. It gets hit by a bat. Boom. Here's the bat. Here's the ball. An impulse that lasts for a very short amount of time, and the ball then takes off, leaves the bat, and takes off this way after the impulse is over, takes off this way at, let's say 52 meters per second. Let's say the baseball has a mass of 0.145 kilograms. I've been teaching this a long time. I know the masses of baseballs, hockey pucks, footballs, those kinds of things. It's kind of fun. But anyway, so what's its change in momentum? Its change in momentum, P, would equal the incoming negative 0.145 mass times velocity times 45. So I'm putting I factored the negative out of there. And I'm doing it backwards because it's the momentum after. It's your final momentum minus your initial momentum. So there I go again. I got in trouble again because I wasn't paying attention. So the change of momentum would be, well, let's just put the 0.145 because that's in both of them, would be the 52 minus -45. So I wind up with 0.145 times 97. Is that right? 97 meters per second. And so this change of momentum is equal to, and you're gonna do some of these problems, and it's huge forces, right? 0.145 times 97 is equal to 14 kilograms meters per second. There's no fancy word for momentum either. Momentum doesn't have, like when we talk about force, we talk about newtons, we talk about kinetic energies in joules, gravitation energies in joules, or if we're looking in other sciences, maybe calories. So that's the big idea. Now, one other big idea I want to tell you about is this. When you take this average force is equal to this change in momentum divided by the duration of the collision. Look what happens. We all know that if this force is equal to the change in momentum and the time is big, then that means the force gets small. But if we have the same thing where we've got the change in momentum and the time is really small, in other words, if I divide by a really, really small number, then my force gets huge. And this collision between a bat and a ball doesn't last long, so it's got a tremendous amount of force. Okay.